What's up, everybody? Mr. Gill here with part 2 of chapter 6. You saw part 1 of chapter 6 that focused on molar heat by analyzing dissolution. This time we're going to find the molar heat of a reaction looking at neutralization. So again, the idea here is you have an acidic solution and a basic solution, both at the same temperature. They're going to be mixed into the calorimeter. Upon contact, they're going to react and neutralize each other, and when they neutralize each other, either energy will be used to do that neutralization or energy will be released into the surrounding water. Either way, the temperature of the water is going to change, and we can measure that temperature change to figure out, go backwards and figure out what energy was released by the neutralization or absorbed, and then of course find the molar heat of neutralization. So let's see that with an example here. So the example is very simple here. It says we want to neutralize 100 milliliters of a 0.6 moles per liter solution of NaOH with 200 milliliters of a 0.3 HCl solution. Both solutions begin at 22 degrees Celsius when they're mixed in, of course, and the final temperature of the solution is 26 degrees. So find the molar heat of neutralization for NaOH. Okay, so most of these steps you're going to see are the same as for the dissolution one, but step 1 is different, and I want you to pay attention here. When you had the dissolution, it was very clear how much water was in the calorimeter. This time, not so much. But we can actually do some math and figure it out, and of course with some assumptions. So first thing to realize is that these are very dilute solutions. 0.6 moles per liter and 0.3 moles per liter, not very concentrated. So because they're very dilute solutions, they're basically just mostly water. And if they're just basically mostly water, we're going to assume that the density of these solutions is basically that of pure water. So their density is about 1 gram per milliliter. So if you have 100 milliliters of a solution which has a density of 1 gram per milliliter, that's basically 100 grams. Same thing for the HCl solution. If you have 200 milliliters with a density that's about 1 gram per milliliter, that's 200 grams of solution there. Now, since we're taking both those solutions and putting them into a calorimeter, the total calorimeter is going to have 300 grams of liquid water before the reaction starts. So 300 grams of water, 100 coming from the sodium hydroxide solution, and 200 coming from the HCl solution. You mix them together, and that is 300 for your calorimeter. That is the important step for molar heat of neutralization that does not happen when you're looking at dissolution. The rest, however, you're going to see is quite the same. So again, we're going to look at the water. We know there's 300 grams of it now, based on our assumption. We know that the temperature change was 4 degrees. It went from 22 to 26 degrees Celsius. And we know the specific heat capacity of water is 4.19. It gives us Q is 5,028 joules, which is the energy that the water absorbed. But you may be thinking, well, sir, how are you using 4.19 as your specific heat capacity? Because it's not really water, is it, right? It's an acidic solution and a basic solution that have mixed together. Is that really water? Well, you're absolutely right. The specific heat capacity is most likely not exactly 4.19, and most likely it's different. But like we said earlier, we're assuming that these solutions are very dilute. And since they're very dilute, they basically behave like pure water. And therefore, we're assuming that the specific heat capacity won't change. And so we'll use 4.19. Now, of course, if there's a situation where the acidic and basic solutions are more concentrated, you may be given some sort of other specific heat capacity to use. But for now, we're going to assume that it's dilute enough, stick with 4.19, and we get our energy that's absorbed, 5,028 joules. That's how much the water absorbed. Well, if that's how much the water absorbed, that must be exactly how much energy the reaction or the neutralization released, because where else did the water get the energy from? In an isolated system. So we know the neutralization must have released 5,028 joules. Okay. Now, again, going back to the idea of what molar heat of neutralization is. Molar heat of neutralization is the amount of energy released or absorbed by a reaction or by the neutralization for every 1 mole. Every 1 mole. Now, last time it was very clear when we were talking about dissolution. Well, obviously it's 1 mole of solute. This time, not so clear. So I want to make sure you understand this part here and take this down. The compound that we always care about for neutralization is the one that we are neutralizing, not the one that we are using to neutralize. So if we go back to the question, it says we want to neutralize 100 milliliters of 0.6 moles per liter sodium hydroxide solution. So the sodium hydroxide is the one that's getting neutralized, and we are using the HCl to neutralize it. So the compound that we care about, and of course it even says in the question, is sodium hydroxide, because that's the one we are trying to neutralize. So we're trying to then find the amount of moles that we have of sodium hydroxide. Now you'll see that you're given the concentration to be 0.6 moles per liter. You were given a volume of 100 milliliters, which you can transform to 0.1 liters. Do your cross multiplication, and you'll see that the moles of sodium hydroxide is 0.06 moles. So at this point, we know that the neutralization process released 5,028 joules if you use 0.06 moles of NaOH. But we don't care about 0.06 moles, right? The molar heat of this neutralization is the amount of energy released for every 1 mole of sodium hydroxide. So you can again do the ratio for yourself to figure out the energy that's released for 1 mole, or you could just go with the formula here. Both do the exact same job. So you do the math, you'll see that you get about, again, negative 83,800 joules per mole. But like I said in the dissolution video, these numbers are going to generally be large, and so this one is a very large number, so we're going to go again to kilojoules per mole. Again, please note, the subscript is N now because we are doing a neutralization. If it was a dissolution, the subscript would have been D. And that's all there is to it. So you can see a little summary here for yourself. Notice the last 4 steps are exactly the same as you saw for dissolution. We just had to do step 1, which was use the density or approximate the density as 1 gram per milliliter to determine how much water we have in the calorimeter. And that's it.